So in part one, we made the case for integration test. And the line I asked you to hold on to was this: bugs live at the seams. The places where production actually breaks are the in-between spaces where code hands off to a database, where objects cross the wire as JSON, where middleware and model binding and authorization, they all have to work together before your endpoint logic ever runs. So unit tests leaning on mocks tend to miss those seams entirely because a mock is only an assumption about behavior. It's not the real thing. So we worked through the shift from the old testing pyramid to the newer testing diamond, where the bulk of your coverage now lives in integration test with a thinner layer of unit tests underneath it it's focused on domain logic, and a smaller slice of end-to-end test on top, maybe with playwright. Then we got into the machinery. We talked about the web application factory, which boots your real application into memory and hands you a client that you can use to make a real-life, genuine HTTP call against it. And we talked about test containers. They let you spin up a real database, a SQL Server, Postgres, whatever you need. It's inside Docker, so your CI pipeline can run against a real thing instead of a mocked repository. And then we spent some time on the problem of lifecycle management. So why inheriting directly from a web application factory tends to create this invisible ordering, this confusing collisions, and why a composition-based approach with 4 explicit phases: start database async, build factory, materialize host, and seed async gives you a setup that's actually readable months later when you actually have to come back to it and change something. A quick word from today's sponsor, Authorization Hub. Everything we're about to build assumes that you've already got authorization logic worth testing: policies, roles, claims. Authorization Hub is where a lot of that logic can actually live. It's a plugin for your existing ASP.NET Core web apps that's not a hosted service. You can run it, own it, and none of your data ever leaves your infrastructure. The core idea is this: Authorization Hub takes your tenants, your groups, your roles, and turns them into identity claims as a request moves through the pipeline. Claims your authorization policies can evaluate directly. Change someone's role or group membership, and their access changes immediately. No redeploy, no code change. It uses SQL Server, Postgres, or SQLite, some of the same providers we'll be testing against in this series, and it ships with a UI, so your team can manage those users, groups, and roles without building that screen yourself. So that's the foundation. Now in part 2, we're going to build on top of that, and we're going to tackle the problem of how do you test authorization in an integration test. So let's take a moment and let's look at some sample endpoints that we'll be writing integration tests against. And there's 2 of those. The GET endpoint requires an authenticated user. An anonymous request will get rejected. So once you're signed in, you can retrieve a stock ticker's information, and that holds whether you're a regular authenticated user or an administrator. Doesn't matter. Now, the post endpoint's a little bit different. You still need to be authenticated, but authentication alone isn't enough. If you're signed in and you're not an administrator, you're going to fail the authorization check. Only if you're signed in as an administrator will the request actually pass. Now, to test authorization, we don't really want to set up a real identity provider. And besides, we don't have control over something like Entra or Okta, Google, or Facebook in a test environment. So instead, let's focus on the part we do have control over, and that's the authorization code itself. Ideally, we want to keep our authorization separate from our authentication. In our testing scenario, authentication becomes part of the setup, and the authorization, it becomes the assertion. So, in other words, who is making the call becomes part of the arrange portion of our test. It's not something we're trying to prove. What we're actually testing is what happens because of who that caller is. Now, for our integration test, we need control over who's signed in when the test runs. And the way we can do that is with an authentication scheme. So, what is an authentication scheme exactly? It really comes down to 3 parts. First, there's a name, and that's just a string like a bearer or cookies. It's a dictionary key and really nothing more. And second, there's a handler. That's the part that actually reads the credentials from the request, validates them, and produces a claims principal. And the third, there are the options. That's the configuration for how that handler behaves. Things like a JSON Web Token signing key or a cookie name. So every authenticated request is going to go through the same 3 steps. And this diagram is really what the whole testing pattern is hanging off of. Authentication asks which scheme should handle the request. And the scheme does the actual work of producing an identity. It reads the credential and it hands back a claims principal. That's the who of authentication. Authorization then takes that identity and judges it against a policy like require role. And here's the part that makes this whole approach work. Only step 2 is faked. Step 1 and step 3 run exactly the code that they would in production. We're not bypassing authentication. We're not short-circuiting authorization. We're just swapping out the one piece that would otherwise require a real identity provider sitting behind the test. And so that's where that 401 and that 403 come from. And it's worth being precise about it because if no identity comes out of step 2, right, no claims principal, then the request never makes it to a policy check. So you get a 401 unauthorized. And if an identity is present, but step 3's policy rejects it, well, then you're going to get a 403 forbidden. The boundary between those 2 status codes sits exactly on the seam between steps 2 and 3. And keeping that seam intact is the whole point of faking the middle one. So let's look at the handler itself, because this is the entire fake. So a real authentication handler is going to read that credential off of the request and validate it against some external authority. Ours is going to do something much simpler. It's going to read a single header, xtestauth. And then it's going to manufacture the identity right there on the spot. And that's it. That's the whole substitution. So let's walk through this method. The first thing it does is check to make sure that the header is going to exist on the request. And if it's missing or it's blank or it returns no result, which is going to mean it's anonymous. No special anonymous logic, no flags, just the absence of a header. Now, if that header is there, then it decodes it. And that header value is just base64 encoded JSON. And it contains the scheme name plus a list of claims that we set up back in the test. The handler decodes that payload and pulls claims out of it, and it builds up a claims identity. The detail that matters here is that it tags that identity with the real scheme name, not a fake one. Then it wraps that in a ticket and returns success, and that's it. It's done. One method, no external calls, no token validation, no signing keys, no identity provider. That identity literally just travels the request as a header and gets decoded into every claim on every call. And from that point forward, nothing in that pipeline can tell the difference. The authorization policies, the anti-forgery checks, anything that inspects the principal, it all sees a real identity under a real scheme name. And that's what makes this step 2 so awesome. Everything downstream runs for real, and it just got its identity handed to it in a different way. So that header is doing double duty, and that's the entire trick. So this registration is going to happen once for the whole host. We set the default scheme for our policy, and we wire up its selector to inspect every request and register cookies and bearer pointing at the exact same handler class, because the handler doesn't really care which scheme was invoked. It just decodes the same header either way and tags the identity with whatever name it was called under. So one piece of code, 2 real scheme names. So now let's just zoom out. Authentication still runs, a scheme still gets selected, the handler still gets invoked, the claims principal comes out the other end. It's just that our handler, instead of using Azure AD or Identity Server, whatever, it's just using that header. The routing and the policy evaluation are completely untouched production code. And that's what makes these tests trustworthy. They're exercising real authorization logic, not a simulation of it. So let's talk about those persona builders, because I've set up a builder pattern for personas, and it comes in 2 parts. Our builder picks the scheme, JSON Web Tokens authentication or cookie authentication. The claims builder, composes the actual identity. And here's what that's going to look like from a test perspective. The whole point of this is vocabulary, not mechanics. As admin states intent, so the test reads like a scenario, not like raw claim writing. And here's where the intent actually meets the policy. As admin is the connective tissue, it emits the exact role string, administrator, that your policies require role check is actually looking for. If that string ever drifts out of sync with what the real policy expects, the test fails honestly, which is exactly what you want. And the build at the end that's just a trigger. It's what actually runs to produce the identity, which means from the test perspective, standing up a fully formed admin persona is just one readable line. Cheap to write, easy to understand, and easy to reuse across every test that needs one. All right, now let's cover Csrf token handling. Since Antiforgery was one of the middleware schemes that we called out way back in part 1, it's the same philosophy here as with authorization. We're not going to fake the protection itself. We're going to exercise it for real. And here's part of the extension that gets us a real token. With Csrf token async makes a real GET request against a real anti-forgery token endpoint that gets back a real token. There's nothing manufactured here. And unlike our authentication handler, right, notice it reads the header name off of the server's actual response rather than hard coding it. So the test follows whatever your anti-forgery configuration really says, not what we assumed it would say. It removes any existing header before adding a new one, which just makes the method safe to call more than once on the same client. Now the failure mode is worth calling out too. If that endpoint is missing, or it comes back with no token, this throws immediately. That's deliberate. A silent failure here wouldn't look like a failure at all. The test would just keep passing. And for a reason that has nothing to do with Csrf protection actually working. The mirror image is the method that proves that the protection is actually doing something. Without Csrf token, strips the header out. A brand new client was never going to have one anyway, so calling this is often redundant and it's just really purely mechanical. But it's not there for the mechanics. It's there so that anyone reading the test knows immediately the missing token is the point of the test, not an oversight. And then there's a pair of methods that exist to keep Csrf out of the way for every test that isn't actually about Csrf. Has Csrf token is really just plumbing for a method underneath it. Post with Csrf async is the one that you'll actually reach for most of the time. It guarantees a token is present when you post your JSON in a single call. This is exactly the kind of thing worth folding into a shared request helper, so a test about authorization, like the Alice test we wrote earlier, never has to think about Csrf at all. It just posts and asserts on the thing that it actually cares about. It's also worth noting that where this actually matters in practice, Csrf protection really exists to defend cookie-based sessions. A browser attaches cookies to a request automatically, which is what makes forgery possible. It doesn't automatically attach a bearer token sitting in an authorization header. So in practice, this is a spot where you'll reach for the cookie persona builder over the JSON Web Token one, because that's the flow Csrf protection actually exists to defend. Same shape as every test we've written in this series. You arrange the client, you act against a real endpoint, assert on a real response. The only thing that changed is which piece of the pipeline is under test. Now put together, a pair of tests for Csrf itself is going to look like this. Let's look at the actual test built on top of all of this. In this case, we're testing the add stock endpoint, and we want to confirm that it returns a forbidden result when the caller is authenticated, but not an administrator. And we start by creating our client with a JSON Web Token authentication as a persona named Alice, built with no admin claims, so nothing that would let her create or add a stock. Now from there, we can post the request as JSON to our stocks endpoint using a shared helper, something like create request. And that keeps this consistent and reusable across a lot of our tests. We get a response back, and then we can assert that the response's status code is forbidden. That's it. It's simple, it's readable, but underneath it, it's exercising the real authorization pipeline, the real policy evaluation, real role checks with only the identity itself faked. A very small amount of test code buys real confidence that the unauthorized users actually get turned away. So now that we have a way to test authorization, let's think about how we want to actually structure our tests going forward. We're going to work with two base classes, and the first is the Web App Fixture base. It implements IAsync lifetime. The interface XUnit uses to manage the start and end of a test setup. This is where our four-phase process lives: starting the database, configuring the pipeline, building the host, and seeding the database. It owns the expensive, long-lived state, the stuff that's costly to spin up and worth reusing across tests where possible. Now, it's an abstract class with concrete implementations underneath it for SQLite or for Postgres, depending on which provider a given test suite needs. Now, the Web App Test Base is the second class we're going to talk about. And this is the class our actual test classes inherit from. So XUnit builds a new instance of this for every single test. So it's the natural place to hold per test state, like the iTest output helper for logging. It also borrows the fixture, the SQLite fixture or the Postgres fixture, through constructor injection and forwards access to it. That forwarding is what gives us methods like createClient, helpers like a stock list for setting up test data, and execute dbasync, all callable directly from the test itself, so a test can just write createClient rather than fixture.createClient. And the distinction matters. The fixture is the expensive part, built once and shared. Web App Test Base is cheap, built fresh per test, and the whole job is to provide an ergonomic, low-friction access to that shared expensive fixture. Now that all of the individual parts have been discussed, let's look at how they actually come together using the test for our add stock endpoint as an example. The first thing worth noticing is that the class is abstract and it's generic over tFixture, constrained to do anything that derives from Web App Fixture Base. That constraint is doing real work. It's what lets every test method in this class run against either the SQLite fixture or the Postgres fixture without writing tests twice. Every test here is written once against that ergonomic surface that Web App Test Base gives us, createClient, not fixture createClient. And it never needs to know which database is actually sitting underneath it. Now, before we get into the authentication, there is a small helper that's worth calling out. The create request function just uses AutoFixture to generate a random ticker and a random price for every single test run. That matters more than it looks like it should, because if every test hard-coded the same ticker, you'd risk tests quietly depending on each other or masking a bug that only shows up with a particular value. Random data on every run means that each test is really standing on its own. This is the happy path, and it's a clean arrange, act, and assert. We arrange a random request and a client authenticated as an admin over JSON Web Tokens. It's all just one line with JWT auth. We act by posting to stocks, and then we assert two things: that we got a 201 created, and that the stock in the response actually matches what we sent. The second half matters. It's not enough to know that the door opened. We want to know that walked through it. These two tests live side by side on purpose. Same admin persona, same endpoint, same request. The only thing that changes between them is whether we called with Csrf token async before posting. With the token, 201 created; without it, 400 bad request. And the cookie auth is exactly the right persona to prove this with. A browser attaches cookies automatically, which is the entire reason forgery is possible in the first place, and that's exactly what we want middleware to catch. Now there's two tests that we have to test for failure, and this pair is really the payoff of treating authentication and authorization as separate concerns. Skip identity entirely, call build with no persona at all, and you should get a 401 because there's no identity for authorization to evaluate. Show up as Alice, a real authenticated non-admin user, and you should get a 403 instead, a known identity that authorization looked at and rejected. Same endpoint, two different reasons for failing, and the status code tells you exactly which one happened. That's the distinction we set out to get when we said authentication is an arranged step and authorization is the assertion. So we said we wanted to be able to test two databases without having duplicated tests. And this is where it all lands. These two classes are almost nothing. It's a constructor forwarded straight to the base. iClass fixture is XUnit's own hook telling it exactly which fixture to build and share across every test in that class. That's genuinely the entire cost of adding a second database provider to the suite. 5 tests written exactly once in add stock test space now run twice. Once against the real SQLite file, once against a real containerized Postgres instance, exercising the real pipeline, the real authorization policies, the real anti-forgery middleware both times, with nothing faked except who's making the call. And this brings us back to where we all started. Bugs live at the seams. That's the line I asked you to carry all the way from the first minute of part 1, and I think you can see now exactly what that was pointing at. Middleware, model binding, persistence, authentication handling off to authorization, a cookie versus a bearer token. Those are all seams. And a mock was never going to sit at one of them and tell you the truth because a mock is an assumption, not the real thing. Now, everything built across both parts was really a service of one goal: make it cheap and easy to test the Steam instead of testing around it. Part 1 gave us the machinery, a real web application factory, a real database from test containers, and 4 named phases so the order of things can happen in something that you want to read, not something you have to remember. And part 2 points that machinery at the seam most people kind of avoid: authorization. And the trick was never to fake less, it was to fake exactly one thing: identity. Authentication ran for real, authorization ran for real, Csrf middleware ran for real. We just got to choose who walked through the door.